Hi, welcome to our talk, Benchmarking Continuous Time Models for Predicting Multiple Sclerosis Progression, a paper that's recently been accepted to TMLR. So firstly, I'd like to thank the team for all the hard work to write this paper. I'm Alex Norcliffe and I'm at the University of Cambridge, although I was a student researcher at Google when this was written. And a big thank you to Lev Prolieve, Deanna Minchu, Fletcher Hartzell, Catherine Heller and Subhajit Roy for all their hard work in producing this paper. So the problem. We're considering multiple sclerosis. MS is a disease that affects the brain and spinal cord, and it's a lifelong disease of the nervous system. It affects approximately 2.8 million people worldwide, and the symptoms include fatigue, loss of vision, and muscle weakness. There is no known cure, and so the aim of a clinician is to limit progression. So we want to quantitatively evaluate the severity of MS. And to do this, we use the Expanded Disability Status Scale, or the EDSS score. This is a score given by a clinical expert ranging from 0 to 10 in increments of 0.5, where 0 to 1 means no disability, 1.5 to 2.5 means mild disability, 3 to 4.5 means moderate disability, and 5 to 10 means severe disability. And the problem we're trying to solve is, given some existing measurements, we'd like to predict the EDSS score some distance into the future, such as 3 months or 6 months. So what prior works exist using machine learning? So a few exist that use MRI imaging, some use clinical data, but the work that we'll be building on uses performance outcome measures. So this work demonstrated it is possible to predict progression effectively using performance outcome measures, or POMs, and demographic data. POMs are a time series of functional tests that test uh, the subject's ability to do certain physical tests, such as placing pegs into holes or walking 25 feet. So this work constructed a full pipeline, uh, converting the features into a common format under the data pre-processing. It benchmarked a range of models from linear regression up to temporal convolutional networks, and it performed subgroup analysis to see which demographic groups are at the most risk. So this is a diagram from the paper which demonstrates what's actually done. So the blue box takes raw data sets, and then this goes to the orange box, which actually converts these data sets into a common representation. And then the green box is pre-processing that further so that these data sets can be used with machine learning models. Then the purple box is the modeling step where a range of models are used. And then finally, the red box actually takes the predictions and performs this subgroup analysis. So our work is to extend on this, and we'd like to investigate the modeling side more. That was the purple box. And so we decided to use these continuous models so that we can include biological inductive biases into the modeling side. So a short background about the modeling. So we use neural differential equations. This is where we use an ordinary differential equation whose velocity is parameterized by a neural network. So that's some hidden state x, and we have dx dt is f of x and t, where f is given by a neural network, and then we can solve forwards with a black box ODE solver. Now this combines the inductive biases of differential equations as well as the approximation power of neural networks so that we can learn complicated dynamics. But why would we actually want to use differential equations? So the first benefit is that it naturally handles irregular time, since we work with continuous time and instantaneous velocities rather than discrete changes. And secondly, it also enforces the inductive bias that the underlying mechanism is a dynamical system described by differential equations. For example, in biological interactions, such as the immune system, or in epidemiological models. So which continuous models did we benchmark? We looked at 4 continuous time models: the Neural CDE, the ODE-RNN, the Latent ODE, and the GRU-ODE, which we describe further now. Firstly, a pointer notation and batching. So models have parameters theta and context vectors c. So these are features that don't change in time, such as sex or ethnicity. And so where we have f subscripted by theta and superscripted by c, this is equivalent to having those as input to the model. And then to batch, we map irregular times t to regular times s, given by the integers, where we use some function psi as a smooth interpolation, so t equals psi of s. And then to actually batch this, we take a velocity given by f of x and t. So dx dt is f xt. And now we have dx ds equals fx psi of s d psi s. And this means that we get the exact same solution. But now all the times are in some regular space, so we can train in batches efficiently. This is also shown in the diagram, where we have a regular time series in the top left, but that's rotated, and the irregular time series in the bottom right. And we can see that the top right panel is showing how to map from S to T. So one of the first models we tested was neural control differential equations. This is where we interpolate all of the observations with some x, and the dynamics are given by DHDS, our hidden state, is some function of h and t multiplied by dxds. So that's a matrix vector multiplication. So f actually outputs a matrix in this case. So what we do is we embed the first observation. So h0 is some encoding of the first x at 0. We run the dynamics in this latent space, and then we decode to predict the label. And here is a diagram of that. So we have capital X are our features and some smooth interpolation of those. We embed the first observation, we run some dynamics in H, and then we decode those. The next model we tested was ODE-RNN. That's where the hidden state evolves continuously, but then there are discontinuous jumps at these observations. So the dynamics are given by dHds is some function times d psi ds. In this case, it's a vector times a scalar. And so we have the initial hidden state at 0. We run the dynamics, so we solve these continuous dynamics up until the next observation. Then there's a discontinuous jump, and then the dynamics are solved again up until the next observation. And then finally, we predict the label. The reason we might evolve continuously and then have discrete jumps is because our belief about what's going on changes continuously, but then once we have that observation, we have a discontinuous change. So if we now focus on the green trajectory, we can see it evolving continuously between the observations, but at the observation points, there are these discontinuous jumps. Our next model was the latent ODE. So here we encode an entire sequence and then use another ODE to decode. So it's more like an encoder-decoder model. The decoding dynamics are given by f times d psi ds. So we encode the whole sequence using an ODE-RNN and take the final hidden value. And then we run decoding dynamics, and then we predict the label with a decoder. And so hopefully it's clear here that we take the whole purple trajectory, encode it entirely with an ODE-RNN, and take the last value as the initial state of our of our latent state, run a new decoding set of dynamics to produce the new green trajectory, and then use a final prediction layer to get y. And then finally, we test the GRU-ODE. This is where the hidden dynamics emulate a continuous GRU model. So that's given here by these 4 lines of equations. And then finally, we use the same set of instructions from the Neural CDE. So we embed the initial observation, run the dynamics, and predict the label. And that's shown here. So on to some results. So the experiments that we did was we test the models on the publicly available multiple sclerosis dataset called Multiple Sclerosis Outcome Assessments Consortium, MSOAC. And we test these continuous models against the best performing model from Roy et al., which was a TCN. So in this table, what we have is we're predicting this EDSS in prediction windows up to 6 months and then 6 to 12 months, 12 to 18 months, and then 18 to 24 months. And the tasks are split into 4. So the first task is predicting the EDSS as a regression task. The second is predicting the EDSS whether it's greater than 3 or not, so as a binary classification task. The third is predicting whether EDSS is greater than 5 as a binary classification task. And then the final task is predicting EDSS in those 4 severity categories, 0 to 1, 1.5 to 2.5, so on. And what we can see is that the Neural CDE typically beats the TCN, as we might expect from our intuition about enforcing these inductive biases. However, the ODE-RNN, Latent ODE and GRU-ODE are not able to consistently outperform TCN. There are some points that are underlined where they do, but they tend not to. However, we see that the Neural CDE is able to beat the TCN. We also ran an ablation where we standardized the features, and we also tested what would happen if we filled missing features with interpolated values or with mean values. So that's shown at the top. So we have with standardize or without standardizing, and we have with interpolating and without interpolating. And just to make it clear that that's where we fill a missing feature with an interpolated value, we always use interpolations for the continuous batching. And what we see is that standardizing features is really important. So the first 2 left columns are far more important than the far better performing than the far 2 right columns. But once we have standardized, using interpolated features doesn't really matter on a performance level where we're filling missing features. And then another ablation we did was testing what interpolation scheme we use. So we used a linear scheme, the natural cubic scheme, the Hermite cubic, the monotonic cubic, which is where we enforce zero derivative at measurement points, and then the rectilinear and recticubic interpolation schemes, which are introduced in Morrell et al. 2021. And what we see is that actually the choice of interpolation scheme doesn't really matter. The best values are spread relatively evenly across all the table. And this is consistent with the findings from Morrell et al., that the choice doesn't really matter, and that the dynamics function is able to account for those changes in the interpolation scheme. So in summary, we extended an existing paradigm for modeling MS evolution by focusing on the modeling side using continuous time models. We benchmarked 4 continuous time models on the public MS dataset, and we showed that if a model is well tuned, then it can outperform these discrete time models or the current best performing one. The impact is that we can show that these continuous models can improve performance as we might expect, and we're opening a gateway to further research on this topic. Future work might be to continue testing on further datasets such as Floodlight, and to parallelize the interpolation process so we can scale to more features and larger datasets. Thank you for listening. We look forward to any questions. If you'd like to contact us, our contact details are in the paper. Thank you.